Hello everyone, welcome back to Tales of Chemistry. Today we are discussing aliphatic ethers. So this is a part of chapter alcohol phenol ether for class 12 ISC chemistry. In this episode, we are mainly learning what ethers are, how to name the ethers, preparation of ethers, and some of the chemical properties of ether. So, ethers have the functional group, a single atom of oxygen. So, this is how we write the functional group of ether. It's just a single atom of oxygen. General representation of ether can be ROR, that is, on both the side of the oxygen atom, you find identical alkyl group. Then we call them simple ethers or symmetrical ethers. So this is a simple ether, but the group on both the side can be different. In such a case, ethers are called mixed ethers. Regarding the nomenclature, these are the only three compounds that we need to learn the name as per ICSC. So the first example here, CH3OCH3, in the common system of nomenclature, you will have to write names of both the alkyl groups. Here, since it is a simple ether, both side you have same methyl group. So it's named as dimethyl. Dimethyl ether, because both the sides of oxygen, the functional group, you have same alkyl group, which is methyl. The second example given, CH3CH2, O CH2CH3. Even here, on either side of the oxygen atom, the groups remain the same. So these are called, this is called diethyl ether, which is also a simple ether. Now, in the third example, the groups on either side of oxygen are different. One is a methyl group and the other one is a ethyl group. So this is named as ethyl, methyl, ether. I arranged the groups in alphabetic order. So this is ethyl, methyl, ether. Then the IUPAC names of these compounds. In IUPAC name, you need to break the chain and oxygen moves away with the smaller alkyl group. But in first and second case, we don't have to worry about which alkyl group is smaller because they are symmetric or simple ethers. So one of the alkyl groups will take CH3 and it becomes methoxy here. And what remains there? Without oxygen, whichever group remains, its name is written as alkane, meaning one carbon is there. So the corresponding alkane with one carbon is methane. Then the remaining part, CH3O, methoxy. So this particular example is in the IUPAC system, methoxymethane. This is methoxymethane. Okay. Now, the next is CH3CH2O, CH2CH3. Both alkyl groups are identical. So send oxygen with any of the alkyl group just because they are identical. Then The remaining part is the parent. Its name is to be written as alkane. 2 carbons are there. So this will be ethane. And CH3CH2O, that is ethoxy. So this particular example is ethoxyethane. And the last one, this is the only option that we have because this is a mixed ether and oxygen should go with the smaller alkyl group. The bigger one is the parent. So parent is here ethane and the substituent is methoxy. So this is methoxyethane. So this is about the nomenclature of important aliphatic ethers. Now, structure of the ethereal group, the ether group's structure. So ether is written as ROR, but here on oxygen you have 2 lone pairs of electron. So those lone pairs of electrons are represented in lobes. So you can write without the lobe also. Bond angle, if possible, memorize 110 degree is the bond angle. Structure can be asked to draw. Moving on to the general preparation of ether. The first one is a named reaction. It's called Williamson's synthesis. Now, in Williamson synthesis, you can notice here, alkyl halides are X. Alkyl halides are treated with sodium salt of alcohol. Alkyl halides are treated with the sodium salt of alcohol. Okay, sodium salt of alcohol, and the result is an ether along with NaX. Result is an ether along with sodium halide. Now, there are certain examples I have written here. First one, ethyl bromide. And this is sodium ethoxide. Sodium ethoxide and ethyl bromide. Slight heating may be required, say around 330 Kelvin, not beyond that. And the reaction takes place. NaBr is eliminated. This is the Br and this is the Na that we are taking out, and just connect the remaining parts together. C2H5O, C2H5. Name is already known to us. Diethyl ether or ethoxyethane. Another one method of preparation, methyl bromide is taken. Another example, methyl bromide is taken and it is treated with C2H5ONA. Br and Na are replaced as NaBr. Same temperature, around 330 Kelvin. And along with NaBr, we are getting CH3O, C2H5. Now you see, this is methoxyethane. Same methoxyethane can be prepared by using ethyl bromide and sodium methoxide. I interchanged the groups. Sodium methoxide. The same compound, that is CH3O, C2H5 itself, is prepared by combining ethyl bromide with sodium ethoxide under similar conditions of temperature. Okay, so that is Williamson synthesis. But Williamson synthesis has a drawback. Williamson synthesis cannot be applied. You cannot use this particular method of preparation if your alkyl halide is tertiary. Tertiary alkyl halides cannot answer Williamson synthesis. The reason is given because tertiary alkyl halides are susceptible to dehydrohalogenation. What does that mean? Tertiary alkyl halides will undergo removal of HX, dehydrohalogenation, resulting in the formation of an alkali. The result will be an alkali. What is the reason? Sodium alkoxides are strong bases. Sodium alkoxide acts as a base and it encourages removal of HX. So this is very important. This is a give reason question. Williamson synthesis is not applicable when the alkyl halide is tertiary. Okay, so the reason is tertiary alkyl halides undergo dehydrohalogenation in presence of sodium alkoxides because sodium alkoxides are strong bases. So this particular reason has to be compulsorily written. Sodium alkoxide is a base. Now, next method of preparation is by dehydrohalogenation of alcohols. When excess alcohol is heated, so first key point that you're noticing is the alcohol has to be in excess. And you need to treat it with sulfuric acid, which is a dehydrating agent. At 413 Kelvin, alcohol undergoes dehydration to give symmetrical ether. Symmetrical ether meaning a simple ether. Alcohols undergo dehydration to give us symmetrical ethers. Now, how is water removed? So, from one of the alcohol, just remove H, and from the other one, OH, you are eliminating a molecule of water. Now, what remains there is ROR, which is a simple or a symmetric ether. Okay, so one example I can give you here, CH3OH plus CH3OH, the second alcohol, treated with concentrated sulfuric acid at 413 Kelvin, undergoes removal of water. Okay, H2O is a product. Along with that, CH3OCH3. Now, one property of this or one speciality of this reaction is you will be getting symmetrical ether. All right. So these are the different methods of preparation for ether. Now look at this point. In this reaction, that is the dehydration reaction, temperature has to be carefully controlled. Otherwise, alkene will be the product. So that has to be noted. Now, physical properties of ether. Boiling point of ethers are much lower than the alcohols corresponding isomeric alcohol. So when you compare ether and an alcohol which have the same molecular formula, ether has the least boiling point. Reason for low boiling point of ether is no hydrogen bonding is possible in ether, whereas hydrogen bonding is possible in alcohols. moving on, ethers are less soluble in water, but they are highly or readily soluble in organic compounds such as benzene. Now, let's move on with the chemical properties of ether. One such chemical property of ether is the reaction due to the alkyl group. Here we are not disturbing the oxygen, but only the alkyl group on either side of oxygen is disturbed. So the first reaction that we are studying here is halogenation. I am taking chlorination as an example. It can be even bromination. Now, when ethers are treated with chlorine and bromine, as the case may be, in dark. So this is a key point that we need to notice. Reaction is carried out in the absence of light. Then substitution of a hydrogen takes place, because of which you may get either mono substituted ether or a di-substituted ether. Mono or di-substituted ether will be the product. Okay, so that is regarding the chlorination reaction. Let's see the reaction now. Here, the ether CH3, CH2O, CH2, CH3. All right. When that is treated with chlorine in darkness, fine, the product that we get is now, so ether in a dark, when you treat it with chlorine, the alpha position, that is the very next carbon, from the oxygen, that is, this is alpha position. This one is also alpha position, but to differentiate between the two alpha positions, let's call any one of these as alpha dash. So one is alpha carbon, the other one is alpha dash. But in darkness, hydrogens only from the alpha or the alpha dash position will be removed, because of which our product now is CH3, CHCl, then O, CH2, CH3. This is called alpha monochloro diethyl ether. Alpha monochloro, meaning on the alpha position, there is one chloro group. All right. Now, the result of first step in chlorination, when again treated with chlorine, in same condition, darkness itself, from the alpha dash position, we are removing one more hydrogen to get the product CH3, CHCl, O, CHCl, CH3. Okay, so this is alpha, comma, alpha dash. So one of this is called alpha and the other one is alpha dash. Alpha, alpha dash, dichloro. Alpha, alpha dash, dichloro, diethyl ether. Alpha, alpha dash, dichloro, diethyl ether. Okay, this is a very important reaction, a very frequent question also. Now, the same ether, if halogenated in presence of sunlight, UV light, UV rays, all the hydrogen atoms are removed at once. All hydrogen atoms are removed by chlorine atoms. So the result will be CCl3, CCl2, O, CCl2, CCl3, and this is called perchloro diethyl ether. Perchlorodiethyl ether. So it's the same chlorination, but depending on the condition of the reaction, chlorination is different. I mean, one gives you alpha dash dichlorodiethyl ether, and direct sunlight, if you chlorinate, you are getting perchlorodiethyl ether. Now, the last reaction in this episode is reactions due to the lone pair of electron present in oxygen atom. And this is, in other words, called formation of peroxide. See, ether, the structure of ether we have already studied. Oxygen has two lone pairs of electron. You can utilize the lone pair of electron on oxygen to bond with another atom of oxygen in UV light to give you the corresponding ether peroxide. These peroxides are highly explosive. Therefore, it becomes important to notice the presence of ether, remove the ether, the peroxide of ether, okay, before we perform any reactions of ether. Or else, ether need to be always stored in dark bottles so that it has no contact with oxygen. The presence of peroxide in all the samples of ethers can be detected by shaking them with freshly prepared ferrous sulfate solution followed by KCNS solution, that is potassium thiocyanate. KCNS, potassium thiocyanate solution. If you get a blood red coloration, that indicates your peroxide, your ether has peroxide in it. Now, peroxides are explosive, so you need to remove the peroxide before you perform any reaction with ether. To avoid the formation of peroxide, as I already told you, ether can be stored in dark colored bottles. Okay, so that's all in this episode. Stay tuned for more videos. Thank you.